name is Timmy Delage, and I'm a PhD student at MPIA working with Paula Penilla. Today we'll talk about the impact of disk ionization on disk morphology. So 5 years ago, we had this astonishing observation from the disk HL that completely challenged our planet formation theories. And nowadays we don't have one, but we like many observations. So here what I'm showing is like a gallery of some of those observed protoplanetary disks from 2 different surveys. In red, the D-Sharp survey, and in blue, the Odyssea survey. Here, the main takeaways are the following. From radial drift theory, we expect the dust particles to grow and reach the Stokes number equal to 1. Once it's like set, then the dust particles can actually very efficiently drift inward, be accreted onto the star, and therefore be lost from the disk point of view. But here, those observations show us that the clear substructures that correspond to dust particles trap. So it means that somehow some mechanism can trap particles at given location in the disk. And you have like a bunch of mechanisms to do so. And here, and now we'll talk about the magnetic field disk interaction, or also called the dead zone mechanism. So briefly, where is the dead zone mechanism? So the dead zone mechanism occurs because disks are weakly ionized environments. The magnetorotational instability, also called the MRI, cannot be at play everywhere in the disk, and especially when the ionization level is low, the MRI cannot develop, because as a reminder, the MRI is the consequence of the coupling between the magnetic field and the charged particles. Where the ionization level is high enough, then the MRI can develop and generate turbulence. So here's like a very interesting picture, because you can clearly see that the ionization level in your disk will set where you can have MRI active regions, and therefore where the turbulence can be high. And in other regions, the turbulence is going to be low. And then if you step back and are interested into the dust transport mechanisms, actually the dust transport mechanisms are all related to the turbulence. And we believe that we can encode the turbulence into this alpha parameter. So it means that all the dust transport mechanisms depend somehow on this alpha parameter. And I just said that the alpha parameter, if you assume the MRI to be the main driver for the turbulence, should be completely constrained by the disk ionization. So now, if you want to understand how the dust are distributed across your disk, you need to understand first how the disk ionization impact on the alpha parameter, and then how this alpha parameter will change the dust distribution across disk. And this is exactly what we want to do in this project. So we want to study the impact of disk ionization on disk morphology. And to do so, what we do first is to obtain a radial profile for the alpha parameter, which is self-consistently derived from the disk properties and ionization level through non-ideal MHD calculations. And then once you have this alpha parameter, we can use this self-consistent alpha parameter to run dust and gas evolution model and see how the dust are going to be distributed across the disk. So to do so, for the first question, how do we obtain a self-consistent alpha parameter? We developed a code called MHDPI that basically does non-ideal MHD calculations. And the output of MHDPI is like a 2D alpha parameter that is completely consistent and derived from the disk properties that you set and the ionization level. So once you have this self-consistent alpha parameter, you can use this self-consistent alpha parameter as an input for your favorite dust evolution model. So in our case, it's DustPy, and running dust evolution model will allow you to see how the dust are distributed across the protoplanetary disks. So now, as a summary, if you want to study the impact of disk ionization on disk morphology, what you will want to do is like to combine MHDPI and DustPy, and then you will have like a self-consistent picture to address this problem. So now I'm gonna walk you through MHDPI. So MHDPI is the code that we developed and is divided into like 4 different stages. So first you need to determine the disk ionization level. And obviously before this, you need to set disk properties. So here in this talk, the star will referred to is a Herbig star. And as for the dust properties, it's going to be a single dust size population of 1 micron and a dust to gas ratio of 1%. So once you set the disk properties, you can calculate the ionization level accordingly. And once you have those ionization level, you can then constrain the number densities of charged particles. And to do so, we use the semi-analytical chemical network from the Okuzumi 2009 paper. Once you have the number densities of charged particles, you can know where the disk is MRI active and where it is not MRI active. And to do so, we use the By and Stone 2011 criterion. And once you have this, you can finally obtain this 2D alpha parameter map that basically like the output of MHDPy. So how does it look in practice? So in practice, once you have the number densities of charged particles, you can know whether this is MRI active and where it is not. And basically you can draw this kind of like a map here, which is called the MRI-driven turbulence map. And it tells you where in the disk the MRI region is. So basically in the red, you have the MRI region. So this is the region of interest where the turbulence can be high. In blue, you have like the ohmic dissipation regime. And in orange, you have the ambipolar diffusion regime. And then if you assume that the MRI cannot develop at all in the blue and orange region, so you set those values to 10 to minus 4. And also following the local box simulations, you assume like the alpha MRI to be 1 over beta in the MRI region, so in the red region, you can obtain this kind of like 2D map here, 2D alpha map. So here, the color are the following. The darker the region is, the closer it is to the lowest value, which is 10 to minus 4. And the lighter the color is, the higher the alpha is. And here as a reference, the highest level, like the highest alpha is, I think, close to 10 to minus 1. So once you have like this 2D map, you can finally use this as an input for dust evolution model and see how the dust are gonna be distributed across the disk. But before that, because we used a dustPy, which is like a 1D dust evolution model, we actually need to like transform this 2D alpha parameter into like one-dimensional alpha parameter. And there's like 2 ways of doing so, depending on what kind of like turbulence you want to describe for different, depending on like the kind of like dust that you are interesting to describe the turbulence on. So first of all, if you want to describe the turbulence felt by large dust particles, so we know that large dust particles basically are going to be very close to the midplane. They are decoupled from the gas, and basically they do not really feel what's happening in the surface layers. They only care on what's happening locally at the midplane. So therefore, you can use this 2D alpha profile, take the midplane values, and then get this alpha profile that will be consistent to describe the turbulence felt by large dust particles. On the other hand, now if you're interested on the small dust particles and gas, that are more sensitive to surface layers, because like the gas can basically like from the surface layers launch waves towards the midplane, and because small particles are coupled to the gas, the small particles are gonna feel those waves. So now, actually, a better way to describe the turbulence felt by the small dust particles and gas will be like a weighted vertically averaged. And here, the main difference between the red and blue profile is like the red profile is smoother, just because here you have like in the surface layers MRI that can like launch waves towards the midplane and basically make the midplane more turbulent than what it is actually. So once you have those 2 alpha parameters, you can actually constrain different things. So from the red profile, you can constrain the gas viscosity, and you can also constrain the dust settling. From the blue profile, you can constrain the dust turbulence and radial diffusion. Once you have constrained those processes, you can actually run your dust evolution. And obviously, to run dust evolution, you need to assume a gas surface density they're gonna be like static in time. And the gas density that we set is something that is completely derived by our MHDPy code. And basically, how do we obtain this? Is we want the action rate to be gradually constant across the disk. And therefore, this is the gas phase density that we need to make it happen. So once you have this and you run your dust evolution model, this is those kind of like snapshot that you can get. So here, those two plots correspond to the dust distribution, like the radial dust distribution across the disk, and the different color bars. So black means like a low density of dust, and light mean high density of dust. And here you can see two main important things. So the first things, if you look at the 1 million year, if you trace now like the 1 millimeter size particles, so corresponding to ALMA observations, you will see that basically you have like a brighter inner disk, and with like basically like a very faint or almost like no outer disk. So here is kind of like a halo shape where the inner disk is bright and the outer disk is very faint. And now if you do the same, if you now trace micron size particles with sphere, and assuming that the chronograph will be, I don't know, less than like 4 AU, you will see that with sphere, you will actually see like a very faint ring, because here you have like a depletion of dust particles, because the fragmentation is very non-efficient in this region because alpha is very low. So growth is very efficient. But here, the fragmentation is very efficient because alpha is high. And here you see that basically, if you do observation, you will see like this kind of very faint disk. And this is very interesting because if now you step back and look at this Odyssey survey, you have like those two disks that present and display this kind of like halo structures. So maybe the dead zone mechanism can produce those kind of observed substructures. All right. So now I'm going to leave you with my conclusion. I want to thank you very much for watching my talk. And if you have any questions, please email me or reach out.